Hi there, we're going to explore how to make a parabola, but instead of graphing a parabola and looking at the focus in Directrix, we want to see how the relationship between the focus and Directrix forms the parabola. So when we have a parabola, it's a shape like this. We'll go over some of the ways it's used in science and in life. Think of the path that a trajectory of a ball being thrown is in this shape. We have a point up here called the vertex, and above it there's what we call the focus point. The same distance below would be a line called the directrix line. So we're going to use these ideas to form a parabola, sort of backwards. Anywhere on the graph, the point here, the distance to the focus, is always going to be the same as the perpendicular line going straight down to the directrix line. So, first of all, the word focus point is sort of the point of convergence, the meeting point. It's what focus means. When a satellite has its antenna here, the signals hit and always go to the focus point. So the sound waves, if it's a microphone, or if it's a satellite, the radio waves will hit the parabola and go to the focus point. The word directrix is really a line of direct motion, or a line along which a point moves. We'll see how we use it. And the word parabola itself is Greek for comparison, a comparison. And so let's take a look using our tracing paper. This is a fun activity to do. I'm going to use large tracing paper. You could use the little patty paper and fold it in half. That's the first step. And I used 1/2 centimeter markings. I'm going to use an inch ruler, so I'll use 1/4 of an inch markings. So the first concept we're going to be using is, how do we find the middle of a line? Because if the focus and directrix are even, if I have a straight line, how do I find the middle without a ruler? Well, I can fold it. If I line up the 2 points, when I fold it, it's going to make a nice line that's a perpendicular bisector, and it will cut my line in two. So we're going to use that idea in order to create a parabola. So start with your tracing paper, and I like to use the middle of the paper, so we could just fold it and make a crease. We're going to be doing this a few dozen times. You can pick anywhere on the focus. You can even explore, have some students make the focus and directrix far away. Other students can make them close. So this is my focus point. I'm going to start with that. And I'm going to use the bottom of my paper to make sure my line is parallel. And I'm going to make a directrix line. So I'm going to line the ruler up, kind of like a number line where there's 0. And I'm going to make a mark every 1/2 or 1/4 of an inch. But I would recommend, if you're using centimeters, every 1/2 centimeter. So on a tracing paper, that'll be about 13 marks in each direction if you're using a patty paper. And I'm going to do the same thing to the left. Now, doing this in class, I recommend you number them. It kind of helps the students keep track of their folds. So I'll just number a few to get an idea. And I'll number the other directions. You don't have to put the negative sign. We're not really using this as a number line. So we're ready to begin. What we're first going to do is take the 0 spot and fold it on top of the focus. Now we could see when it's not lined up. A marker might be nice. So for example, we could see the focus is there, it's not lined up. We want to line it up perfectly, right on the directrix where the 0 is. And I'm going to make a fold. So now we have a perpendicular line, and that's actually going to be our vertex. We can label that later so students don't accidentally fold it on top of the vertex, because I've even done that. So the next step is going to be repeated over and over again. I actually recommend you turn your paper backwards, then you'll see the numbers. They'll face the right way when we fold it. So I'm going to now line up number 1 on top of the focus, but not the number 1, the actual little Directrix line marking. And when I do that, I'm then going to fold it. Make a careful crease. And you actually don't have to keep opening and closing your paper. If you hold the back with one of your fingers, you can sort of slide it over. And now I put number 2 on top. Let me zoom in a bit. So we can see that focus line. I'm folding number 2, and I fold the whole crease. Then I line it up to number 3. And I'm going to continue this process until I've folded every single space. So now I'll go to number 4. And I'll probably speed this up so you don't have to watch me do it. So now that I'm done, you can start to see the parabola formed. I have one side completed, so the other side is going to finish. I'm going to repeat the process. So now I'll flip it back over. Now I'm going to fold the other side. Start at 1, line it up, and fold it. Then go to 2. So I do notice that when you're folding the second side, because the paper's already creased, it is a teeny bit harder to line them up. You just have to be patient. And go through each step. 1, 2, 3, 4, 5, and all the way to the end. If I put something darker behind it, you can see clearly the parabola being formed. And you could have students trace it with their pencil. So when we first folded, the middle one, it would have been right here. Oops, I'm sorry, right here in the middle, obviously. That's the vertex. It's where the T is. I accidentally marked it here. The distance from here to here is the same as the distance from here to here. So what we achieved here by folding it is we found the middle spot, the middle from the focus to the Directrix when they're even. And so what that tells us or shows us is at any point from here, perpendicular or straight down to the Directrix, is always the same distance to the focus. And that's true anywhere on the parabola. So that's part of the definition of a parabola. I could do the same anywhere. Here, if I go directly down, the distance from there to the focus will be the same. And we can measure it. So here I have 4.5 inches almost. And here I have 4.5 inches also. So this is really how a parabola is formed or created. The focus to the parabola and that same point to the Directrix is congruent. And you know, another thing that we achieved with these folds is we created tangent lines. So for example, if I trace one of the folds, it's going to create a tangent line. So you have this beautiful pattern down on the bottom of symmetric lines. So we have this line, each of the folds is what we call a tangent line, which is the slope or rate of change at that particular spot. So let's say you had a parabola of y equals x squared. In calculus, we start to learn about derivatives. The derivative would be 2x. So you could plug in the x value to find that slope, that rate of change. If you really wanted to get more into it, we could make markings using 1/2 centimeter, or in my case, 1/4 of an inch, and actually find the equation of the parabola. We could find the vertex, put it in our formula, find one more point, and actually plug that point in and find the equation of a parabola. But this, to me, is a very unique, wonderful way to take a look at how a parabola actually is formed and what the directrix line really is and how it's used with the focus to create the parabola and the reverse. You see parabolas all of the time. You see them in rainbows. You see them on arches, like the McDonald's arches, architecture, that's the Eiffel Tower, roller coasters. You see it in the trajectory of shooting a basketball or throwing any ball. So you do use them a lot, and some of the practical uses in science would be parabolic satellites. So the satellites pick up signals, and the parabolic shape allows the signals to hit inside of the bowl or cone shape or bowl shape and bounce to the focus point, which is where the main radio receiver is. We also use that, even spies use it to pick up conversations from far away. It's called a parabolic microphone. And you may have seen people on sporting events holding a parabolic microphone, and it allows them to pick up the voice of the players even though there's a noisy stadium. So it sort of directs the sound of whatever it's pointing at. It will direct that sound and pick that sound up mostly and sort of drown out the crowd. So it is very important in science and technology, but we use it every day. Every time something's thrown, it follows a type of parabolic direction. So another thing is kind of seeing what we did in our tracing paper and what it would look like digitally. So digitally, we have our directrix line and we have our parabola, and like we were saying, the focus and the position from the focus to the point on a parabola P will always be the same distance as the line perpendicular to the directrix. So this top D red line and the bottom D red line, they're always equal. So it's really almost forming an isosceles triangle. And so what we did with our tracing paper is we found multiple spots that when we folded them found where the directrix and the focus meet, where the middle is. And by doing so, we created, through folding, a parabola. So that could help you understand. I know I didn't quite understand what is a directrix line, how is it really related to the vertex, and what is the focus. And we do say that they're equal distances, but this is sort of what it means visually. So hopefully it helps some of us understand what a parabola is and how it's formed a little better. Example would be a headlight. So the headlight's shaped in a parabolic shape to be able to point your headlight in the direction you want it to go. And for a car, it'd be pointing it forward. So certain types of light bulbs, even speakers, will do the same thing. So hopefully you can look around and start to notice the parabolas and how we use them quite often.